So let me introduce a concept here. So suppose you have two probability distribution, one denoted as pi and the other denoted as theta. So pi is equal to some P1 Ps and Qs. So we are going to write this to mean so what is the maximum possible value of this norm pi minus theta? Quickly. What will be the maximum possible value? Number. I want a number, 2. And when will it be 2? If the support of P and support of Q is disjoint. So P is putting probability on some of the i's and theta is putting its probabilities on the complementary set. And that's the maximum possible value. You know that. Okay, good. Okay. So this is the notation that I will need. Now I'm going to state a very interesting result. Let's see. Okay, here it is. Now, if we have a transition probability matrix P, each of its row represents a probability distribution on the set A, right? So each row of P, each row of P is a probability on A. So A is the state space. So I think we can make things simple to assume that A is just S. Right? Each row represents a probability distribution because it's a stochastic matrix, so it's a probability distribution. Okay. So now I'm going to define something. Okay. So I'm going to define a constant Cp, which is defined as 1/2, or let's say max. So let's say I denote the rows of P as phi1. These are the rows of P. So max of half phi I. Is it meaningful? It is meaningful because phi I is a probability distribution like pi. Phi j is also a probability distribution like theta. So I take that. So I take any two row, look at the difference between those two probability distributions, look at their norm, and I put a half here because I want to have it bounded by 1. You have already said that the maximum possible value of that is 2, so I put a half there. And it is the maximum of all such things over I and j. Cp is called the contraction coefficient of P. So clearly Cp, what is the bound on Cp? Cp lies between what and what? Certainly it is greater than equal to 0 and it is less than equal to 1. Something more is true. if I have a transition probability matrix like the one that I have assumed, what did I assume about my transition probability matrix? All entries are positive. Then something more can be said about CP. CP is always going to be strictly smaller than 1. And it's very easy to prove that. It's kind of a little messy computation, but conceptually it's extremely simple. Okay? Those of you who know the proof, you know the proof. But those of you who don't know the proof, I ask you to try the proof first by taking P to be a 2 by 2 transition probability matrix. Then you will see it immediately. And once you see it for 2 by 2 transition probability matrix, generalization of that into any dimension is very easy. Okay? So for a strictly positive P, so if P is greater than 0, then CP is strictly smaller than 1. In fact, there is a very nice bound on CP. Let me write that down for you. So here is the bound. Let's see. CP is less than or equal to 1 minus max. No, right, it should be minimum, right, not max. Minimum of the entries of P. So if you take the smallest entry, so certainly if I have a completely positive stochastic matrix, the smallest entry is going to be positive. So 1 minus a positive number, so it's strictly smaller than 1. It's simple algebra to prove that. Okay? Keep that in mind. So for a strictly positive stochastic matrix, contraction coefficient is strictly smaller than 1. Now we will see in a minute why it is called contraction coefficient. So it must be operating as a contraction constant. Okay? So it must be a contraction constant associated with some operator. Obviously, what is the operator? Okay? The linear operator must be the transition matrix itself. And let's see that. So here is the result. I've used theta. I can talk about that, right? I operate P on pi. I operate P on theta. That will give me two different probability measures. This is always going to be less than equal to Cp So now you understand why it is called a contraction coefficient. And it follows straight from this definition. So once again, if you want to prove it, first try to prove it for a 2 by 2 transition probability matrix. And then you will see the proof. All that it requires is the fact that P is a stochastic matrix, so its entries are all positive and they add up to 1 along a row. So this is a beautiful result, right? Because now you see that you can use it to prove all those limiting results very nicely without knowing anything about what is the Markov chain. It's now a property of matrices, results related to matrices. So here is the second thing that's also important. Suppose we have two transition matrices, P and Q. This Q is another transition probability matrix. So if I look at PQ, is that a transition probability matrix always? So the question is, if you don't know what is transition probability, if I give you a stochastic matrix P, I give you another stochastic matrix Q, I take the product, they are of the same dimension so that you can multiply them. Is the product going to be a stochastic matrix? So you only have to check. See, the entries are going to be positive, right? Or non-negative, because you are multiplying only non-negative numbers and adding them up. Only thing you need to check whether the row sum is 1. That is easy. Not always. Is it not true always? Suppose I have an inhomogeneous Markov chain. What is its transition, two-step transition? P1, P2. It must be a transition probability matrix. Otherwise, everything will collapse, right? So it better be a stochastic matrix, okay? But let's say that I don't know about Markov chain. I can verify it directly. It's just very easy. You calculate the entries of a row, add the entries up, and then it is just an interchange of sum, and then you will see that it adds up to 1. It's very easy. So PQ is another stochastic matrix. But what is important or interesting is the fact that C of PQ is always less than equal to CP times CQ. So the contraction coefficient of the product is less than equal to product of the contraction coefficients. That's what matters when you are trying to prove those convergence results. Now suppose I have already proved this. Can you give me a quick proof of this? How? Just sketch the proof. I don't want the details. See, when you are multiplying P by Q, it's like I can take the rows of P. Those rows may play the role of pi, theta, etc., and then it follows actually. Okay? So if this is true, then this will happen. So essentially, to prove this, you use this result. Now, I start with some initial distribution pi.